it looks so simple and easy with the hydrogen. You can produce it with solar and wind, you can store it and you can transport it, but it's also a precious good and it has to be handled with cautious. So this is it's a wide field, the hydrogen economy and how we come to this. And we will not cover the whole aspect of this today, of course, but we will have a look on some aspects which are relevant for the PV industry, particularly for those who might want to sell electricity, maybe via PPA, to green hydrogen plants, or maybe for those who are considering to co-locate electrolyzers with PV production, or maybe even build pure PV electrolyzer wind, maybe hybrid plants which are working off-grid and just generate hydrogen. So there's still a lot to do because it will have to do with the supply chain. One has to see how this market is going to develop. It has to do with the electrolyzer technology because one has to make design decisions and technology decisions. And it has to do, of course, with cost because from the cost development of the electrolyzers, it depends where and when it's worth to invest. I'm very happy that I can welcome George Touloupas as our first speaker. He is an outstanding expert on technology and quality, since long well known in the PV industry, and as the PV industry has proceeded, also in the storage and the hydrogen industry. George Touloupas is leading the technology, quality and intelligence team for PV, energy, storage and hydrogen at Clean Energy Associates, CA. Hello, George. Good morning.
Thank you for having me.
I can hear you. Yes, you have prepared a very packed wrap-up, I would say, of what you need when you want to familiarize yourself with these aspects I have just mentioned: supply chain for hydrogen production, electrolyzers, and hydrogen market. So the stage is yours, and after that, I hope we have some time for Q&As.
Thank you. All right, let's start. All right, as Michael said, we're going to talk about best uses, the supply and demand situation or forecasts, some LCOH and figures, and talk about the quality risks, of course. So very few words about Clean Energy Associates, the company I work for, which is also belongs to the family of Intertech companies since last year. We have more than 225 professionals, experts, engineers, a very long track record of 15 years, and a very big presence, global presence. Our clients are the biggest developers, IPPs in the world, and financial institutions. We have a very solid track record in PV solar, 250 gigawatts, more than 30 gigawatt hours of energy storage system inspections. And since a couple of years ago, we've been active in the electrolyzer space, so the green hydrogen space. And these are the verticals I just mentioned: PV solar systems, battery energy storage systems, electrolyzers, and inverters and transformers. So hydrogen is a notoriously complex topic. So I decided to start with some key figures so that we can touch some realities. So first of all, about the cost. So if you compare hydrogen to natural gas, fossil-derived hydrogen is between $1 and $2 per kilogram. Right? That depends really on how it's produced and the price of fossil fuels. Now, the green hydrogen targets the same cost levels, around 2 kilograms, right? Which is a very ambitious cost target, even by 2030. So we'll see about that for various reasons. Now, if you convert this to energy, $2 per kilogram is $60 per megawatt hour. And if you check the Henry Hub spot price index for natural gas, a few days ago, it was $2.77 per million BTU, which is, if you do the conversions, is close to $10 per megawatt hour. So hydrogen is around 6 times more expensive than natural gas. So clearly, if you burn hydrogen to produce heat or even electricity is a very, very bad idea economically. So it's 6 times more expensive. Now, moving on to efficiency. This is probably more well known, the well, or if you like, point of connection of electricity, well-to-wheel efficiency for an EV is 77% because electricity is so much more efficient than anything else that we know. So these losses are from energy conversion, DC to AC, some losses of the battery round trip, efficiency, and like the motors, but overall it's super efficient. Fuel cell EVs, on the other hand, they have 42% efficiency because there are losses in creating hydrogen and then from hydrogen back to electricity. And if you make synthetic fuels using this hydrogen, so power to diesel, for example, it's only 20% efficiency. So electricity is way more efficient to power vehicles than hydrogen fuel cells. So electrification of transportation is probably a much better idea than using hydrogen. And there are many discussions about range, etc., but let's stick to these numbers for now. Now, if we compare it to liquid fuels again, right, density. Compressed gaseous hydrogen at 700 bar, that's 1.25 kilowatt hours per liter. Now, if you liquefy that, you get up to 2.36, almost double kilowatt hours per liter. To liquefy it, you need to cool it down to minus 253 degrees Celsius, which is very hard and very energy intensive. So a lot of energy losses there. Even compressing it is energy intensive, right? Comparably, kerosene or diesel volumetric density is close to 10 kilowatt hours per liter. So from high compression gaseous hydrogen at 700 bar, liquefied hydrogen is almost 2 times more dense, but kerosene diesel is 7 to 8 times. So even compared to liquefied, which is the densest form, kerosene or diesel is 4 times more dense. So that's volume, right? Not weight. Weight-wise, hydrogen is great, but things that take volume create costs. So big energy losses, by the way, even for compressing at such high pressure. So fuel for airplanes or even ships, big problems because of this volume constraint, also the efficiency constraints. So having seen these key figures, this is a favorite, a very well-known chart, which was created or adapted by Michael Liebrich, and he's had several versions out. This is the latest one, which I saw him present in Rotterdam recently. So that shows the priorities of application. Obviously, at the top of this ladder is the no-brainers and the things that we have to do anyway, no matter what the cost is. So it's fertilizer, hydrogenation, methanol production, hydrocracking, desulfurization. A lot of these have to do with fossil fuel refining, by the way, right? And then it goes down, and at the bottom of the ladder are the least appealing, very expensive, let's put it like that, applications. Somewhere down this ladder, you can see transportation as well, and hydrogen trains or hydrogen bicycles or domestic heating.
George, sorry to interrupt. You have to speed up. You have to speed up a bit. That is
yeah.
also.
All right. Okay.
I see your very interesting slides at the end, so it would be great to come there.
Absolutely, thank you. Yeah, so that was the application conundrum, if you like. So hydrogen can be used in many things, but it doesn't make sense economically for a lot of these things. Another topic is the LCOH, which is the levelized cost of hydrogen. Let's say the dollars per kilogram. That's a very popular metric. When we connect these electrolyzers to renewable assets, of course, the renewable assets don't operate 24/7, so they have a very variable profile. So taking this into account, the capacity factor, so the percentage of full load hours, is never going to be 100%, right? Because if you plug it in the grid, it's not necessarily green electricity. So LCOE plays a dominant role, so the price of electricity, but also the profile of electricity injection, which is really the capacity factor. And of course, the capex of the equipment. So we can see from these charts, the top chart is alkaline system with a very low capex. This is alkaline from China, alkaline systems from China. And at the bottom is proton exchange membrane systems, which are way more expensive, even in China, 3 times more expensive almost. You can see the very different behavior of LCOH. So the red color, which is the good color in this case, the cheap $1 to $2 per kilogram hydrogen, is very difficult to achieve for PEM, even at $20 per megawatt hour LCOE, right? Even at 100% utilization. You see, as the utilization goes up, the capacity factor, that is, then the system price is not so important, the capex. But at low utilization, a low capacity factor, which is where renewables are, probably 30, 40, 50%, then capex is very important. And as you can see, for alkaline, it kind of levels up the red curve pretty early at around 40, 50%. And these are fundamental constraints, as we know from additionality and delegated acts that have already been established in Europe. Now, some supply and demand forecasts. This is a very conservative scenario, which we have chosen to adopt. I have seen much higher numbers than this. Now, you don't see here million tons, you see gigawatts of electrolyzer demand.
You have to speed up a bit. Sorry, we have, I would say, 2 minutes left. Can you do it in this?
Okay, no problem. No problem. Based on this capacity factor, so basically if it's 65% utilization of an electrolyzer system, you need 10 gigawatts to produce 1 million tons per year, right? If it's 40%, you need 16 gigawatts. So that's why we have these curves, 65% capacity factor or 40%. So for lower capacity factor, you need more electrolyzers, basically. And this is the bars, the green bar is the nameplate projection, what the electrolyzer factories will be able to output. And the blue bar is what we actually believe that they're going to be able to output. So there could be an overcapacity of electrolyzer factories, but maybe not. So these numbers, they have a lot of uncertainty in them. But in extreme case scenario, yeah, the nameplate capacity could be double of the actual demand. Again, that's a conservative demand scenario. Now, scaling up challenge. So that's the big problem. 2022, 1 gigawatt of shipments. 2030, we said before, maybe 60, 70, 80, maybe 100. So close to 100, 2 orders of magnitude. So it's never been done before. That's the challenge, scaling up challenge. And a lot of things can go wrong. So we can have problem with the technology choice. It's going to be alkaline and PEM. There are cost issues here mainly, degradation issues too. Quality risks, these are complex chemical factories. You can have leaks and failures and corrosion and systems going off after a few months and getting refurbished. We hear these stories, especially in these mega projects in China, but also in Western projects. And the fire risk it cannot be stressed, right? If hydrogen leaks, even at 4%, you have fire. So it's a very dangerous gas from that respect. And also with alkaline, you have corrosive risk because of the lye. So when these bad things happen, there is downtime, lost production, maintenance and repair costs, safety risk, of course, are very important for human life too. Big reputation damage for the developers, also risk of regulatory non-compliance. So there is a lot of risk in hydrogen, and it mainly stems not because it's a new technology, it stems because of the scale that is unprecedented. This is it.
Thank you very much for this great overview. I think it was really great, particularly this sheet with these many numbers. When I saw it first, I thought, oh, what should all these numbers mean? But you explained it in a great way. We are really late in time, but I want to ask you two questions, and please answer, and maybe in 2 sentences, even if it's not perfect, because we have not more time. One time, for a lot of our audience, it might be interesting what you think of colocation of electrolyzers with PV plants in Europe. I mean, it's region dependent. In Europe, 2 sentences.
Not colocation, same market. That's the rules, the delegated acts. It has to be geographically correlated and time correlation as well. So it doesn't have to be next door. It has to be the same electricity market.
Okay. Next question. I mean, also 2 sentences. We know in PV industry, we know from the module market that it makes sense to do factory inspection, but that is also related to this special product modules where you cannot see all quality defects in the product itself, but you have to check it in the factory, in the fabrication. Is it the same with electrolyzers, and why?
Well, I would compare it to battery systems, which are complex systems, more than PV modules, which are small, modular, simple objects. So it's quite different. These are very big, very complex machines. So you would recommend factory inspections? Of course, CAA makes a business model out of it, but would you recommend it? If I buy an electrolyzer, should I send somebody to the factory? Absolutely. I mean, as I said, it hasn't been done before at this scale, and there are definitely things that can go wrong when we have such a big assembly. Right?
Okay. Thank you very much, George. It was great having you again on our roundtables. See you soon. Bye.
Thank you for having me.
After George has given us some insights into the supply chain of electrolyzers and on the scale-up challenge, we want now to have a closer look to the heart of the hydrogen production plant, the electrolyzer. And for this, we have invited András Perl. He is researcher and lecturer at the Hanze University of Applied Science from the Netherlands, and he focuses on system integration in the energy transition and on hydrogen. Hello, András. Great that you can join us.
Good morning.
Good morning. Let's just start with the topic. Can you explain in simple words, because we are not all technicians here, can you explain us in simple words what the difference is between alkaline and PEM electrolyzers?
Well, I would start what is the common in all the electrolyzers that are commercially available right now, that there are 2 electrodes and electricity flows through these 2 electrodes, and the process to happen, water should be decomposed in hydrogen and oxygen. And the main difference is we have to realize that at one of the electrodes, hydrogen is produced, on the other part of the electrode, oxygen is produced, and we definitely don't want to have them mixed because that's a very dangerous situation. And for that, we have a separator. And in an alkaline electrolyzer, this separator is a porous material where hydrogen or hydroxide ions together with the electrolyte can diffuse and flow through. The bubbles that are formed of the electrodes are big enough so they cannot go through the pores unless there is a high pressure difference between the 2 compartments. So when we run an alkaline electrolyzer, we have to be very careful that the pressure at the 2 parts are exactly the same. While the PEM electrolyzer uses a membrane, quite robust membrane to separate the 2 compartments. And this membrane is not porous, only hydrogen ions are allowed to go through, but water in principle and hydrogen and oxygen are not allowed to go through. And this allows a higher pressure difference. So there are commercially available PEM electrolyzers that operate on the cathode side, that hydrogen is produced at 50 or 100 bar, while at the anode side at 2 or 3 bars. And that is safe and is proven technology.
So you would say it's a safety advantage of the PEM electrolyzers?
Safety, you can operate at higher pressure. It depends on your application, at what pressure you want to use it, but this might decrease your compression costs because you don't need to compress separately your produced hydrogen. And also, I think despite the higher price, the PEM electrolyzers can react a bit faster on a changing or fluctuating electricity.
Let's first stay a bit with this higher reaction, this faster reaction of the PEM electrolyzer. What does that mean if you want to combine electrolyzers with, I would say, a PV wind hybrid hydrogen generator? Is that really that you cannot do it with alkaline? I mean, basically you would have probably something like 3,000, 4,000 working hours a year when you do a PV wind hybrid plant. Can you do it also with alkaline, or would you have to use PEM?
I think alkaline electrolysis, so the technology is a mature technology, and I would say both technologies can be used with renewable electricity. The startup time, the ramp-up rate might be slightly different, but once we start to talk about larger scales, so not kilowatt, but megawatt of multiple of megawatt electrolyzers, I think for both alkaline and PEM, the ramp-up and the startup time will be or could be an issue. But the good side of this that we can forecast the weather nowadays quite accurately, at least in the coming 1 or 2 hours. So if we know that we can expect a lot of sun soon, then maybe using a buffer, some smaller scale batteries, just enough to start up safely the electrolyzers in time, so we can use most of the electricity that's coming from PVs or wind.
I mean, you already mentioned it, that the PEM is more costly than the alkaline. I mean, as far as I know, alkaline are mainly developed in Asia and China and are quite cheap. PEM are mainly developed in Europe and other Western countries and are, I think, factor 3, factor 4 more expensive maybe. So why should I then go to PEM now?
I think the advantage, the pressure difference advantage, the higher ramp-up rate advantage is worthwhile because you can utilize more of your electricity production. When you have a fluctuating electricity production and you have a given ramp-up rate, if you cannot accommodate all of the electricity, then that will be wasted. Or maybe you can sell a part of it. It's easier said than done, I guess. But maybe I should mention the anion exchange membrane electrolyzer. It's also a version of the alkaline electrolyzer that uses cheaper electrode materials and electrocatalysts, but uses a membrane as a separator, not a porous material. So there also the pressure difference is not an issue, and that could be something that follow in the near future.
I think there are not so many companies at the moment working on this technology, and it's not so. It's a bit younger, but it's available on the market. So.
Yes.
Why don't the others also work on this? Do you think that also other developers will switch to this technology?
Okay, I don't have a broad overview of the whole market, but what I see, I do see that more and more companies, at least in the Netherlands, smaller SMEs are also interested in working on developing anion exchange, AEM electrolyzers. So it is coming up.
Yeah. Talking about research and development, what trends do you see there? I mean, it looks that you already said there are mature products on the market. I mean, for all technologies, for all 3 electrolyzer technologies, there are mature products on the market. But what are the next challenges for R&D in this field, and what do you expect?
As it was mentioned in the previous presentation, the scaling up, we want higher and higher capacity and unprecedented increase in capacity. And I think one of the main challenges, how can we achieve that? Just giving an example, should we make or buy several electrolyzers and modular units and then build up from a few megawatt to a gigawatt plant? Or do we want to develop one single stack that is hundreds of megawatts capacity? How can we achieve that? What kind of safety issues will we encounter during that? Or simply keeping the scale, keeping the size, but increasing the current density. I think these are one of the important questions right now.
And in terms of cost developments, we will see just from BloombergNEF in the next presentation following this interview more detailed information on cost. But is there a natural law why PEM should be more expensive than alkaline, or will that also, do you see that also their developments can really drive down the costs?
The most of the PM costs are coming from the rare elements used as electrocatalyst on the electrodes and the membrane assembly. These are platinum, iridium, rare materials. In my opinion, I don't see a significant price drop in the cost for these materials in the future, especially if the demand is increasing.
But maybe you can reduce the content in the electrolyzers itself, which would also reduce the prices.
And the research is going on, and if they can find alternatives that have the same high efficiency but lower costs, that would be a game changer, I would say.
Okay, thank you very much for this interview. This was András Perl, András Perl, researcher and lecturer at Hanze, University of Applied Science. I think it's in Groningen, isn't it? It's in Groningen.
In Groningen,
yeah.
Okay.
Yes. Thank you very much for joining, and have a nice day.
Okay, thank you.
We have seen in this hydrogen session until now what some insights in the supply chain. We have learned something about electrolyzer technologies. Now we'll have a closer look into the cost trends and other industry trends related to electrolyzers. And we will also touch the questions where hydrogen production can become competitive. I welcome Adithya Bhashyam. He is Hello, Adithya.
Hi.
Hi. He is the EMEA hydrogen analyst of BloombergNEF, and he covers policy developments in the region and the development of green hydrogen supply globally. He holds an MSc in climate change management and finance from Imperial College in London, and a BSc in ecological and environmental sciences with management from University of Edinburgh. Yes, we are really looking forward to your presentation with a lot of nice graphs and lines, and please explain it to us.
Of course. Yeah, great to be with you today. All right. Let me just wait for the slide deck to come online. All right. I'm happy to be with you here today and to give you a bit of an idea of how we see the hydrogen market developing over time, both in terms of volumes, but also in terms of costs. Obviously, the hydrogen market has a lot of hype behind it and a lot of interest from governments across the globe. This is something we're tracking. And as of this year, we found that 52 markets or 52 governments have published a hydrogen strategy with another 29 under development. So all of these strategies are setting out a vision for how these governments think the sector should develop. And now every major economy has one of those strategies. A lot of these strategies come with significant funding for the hydrogen sector as well. In total, now we're counting over $308 billion that are available between now and over the next decade towards hydrogen projects of various kinds. $308 billion is about a quadrupling in subsidies available to hydrogen over the last 2 years alone. So that's just showing how much momentum is there behind clean hydrogen already. A lot of this funding is now in the US with the Inflation Reduction Act tax credits for hydrogen, but Europe also has significant funding opportunities for clean hydrogen projects. With this excitement around hydrogen and the funding available for hydrogen, we see project developers announcing more and more projects to produce and use clean hydrogen of various kinds. We track all of these announcements at BloombergNEF, and what we get to is that there's about 174 million metric tons of clean hydrogen production announced by project developers globally. To put that number into context, 174 million metric tons is significantly more than the 100 million metric tons of hydrogen demand we have today, but still not at where we need to be for a net zero pathway. We think for net zero, there needs to be about 500 million metric tons of clean hydrogen demand across various sectors. But still, it's a huge volume of production that could come online. And what's interesting about this volume is that the majority of projects are using electrolysis, so electrolyzers connected to a renewable electricity source, solar or wind, to produce that hydrogen, with just a minority looking at natural gas with carbon capture and storage. If we go to the next slide, what a lot of the success of these projects hinges on is the business case. And the business case today isn't clear. Green hydrogen in the green range here is much more expensive than fossil hydrogen today. So we think fossil hydrogen from natural gas is priced somewhere between $1 to $3 per kilogram today, whereas green hydrogen can be as expensive as $12 per kilogram in the most expensive markets like Japan and Korea. We do think these costs are bound to come down, though, with two major trends. One, the cost of the electrolyzer, the core equipment that you need, needs to come down tremendously from the ranges that we see today. And two, long term especially, the cost of renewable electricity will be really important in driving down the cost of renewable hydrogen below the cost of gray hydrogen. If we look at this by market, the cheapest markets in 2030 that will produce green or renewable hydrogen in these bars are markets where renewable electricity will be cheap, chiefly Brazil, where there's cheap wind energy available. And what we see is that by 2030, in our cost analysis, green hydrogen, at least from intermittent production, will undercut blue hydrogen, and also in some markets with cheap renewables, undercut newly built gray hydrogen plants. Of course, with the commodity price environment and inflationary environment that we're seeing, these costs could be delayed by a few years. And I wouldn't be surprised if next year we say it actually doesn't happen by 2030, but by 2035 or so. But the general trend towards cost reductions is clear. What's also interesting in our cost reduction trends is that by 2030, markets with really cheap renewable electricity might even be able to undercut existing gray hydrogen plants running at marginal cost. So that's what we at Bloomberg call tipping point 2. So building a new green hydrogen plant could be cheaper than continuing to run an existing gray hydrogen plant in the early 2030s or so in some markets. And the real driver behind this is cheap renewable electricity costs. For this to happen, electrolyzer costs need to come down. We're today at a level between $1,400 and $1,600 in Western markets per kilowatt. But in China, electrolyzers already cost a quarter of that. We think in the 2030s or so, even Western electrolyzers will come down in cost to that $400 per kilowatt level or below to match Chinese electrolyzers over time. Again, that might be delayed because of the general macro environment. But in general, we think this trend still holds true. And as I mentioned, if you look at the levelized cost of hydrogen production, much like the LCOE, today, whether you connect to PV or connect to wind, the majority of the cost is the cost of the system, and that is coming down. But over time, the yellow bit in this chart, the cost of electricity, really matters. That's why where you have really good renewable resources and cheap renewable resources, that's where we see the cost of hydrogen production being cheapest as well. For this to happen, we need more incentives for demand. Today, we're seeing that out of all the proposed projects for clean hydrogen production until 2020, only just about 1.3% of these projects have signed a binding offtake agreement with a buyer. And why we don't see enough support for demand is because the business case doesn't work. Subsidies on the production side would help, but particularly also on the demand side, we think there needs to be a lot more support for supporting buyers to sign those long-term 10, 15, 20-year offtake agreements to get these projects off the ground. Once you have that offtake, financing these projects becomes a lot easier. So both what we need as a next step in the hydrogen industry is supply side to bring the production costs down, but also demand side support to help buyers switch to clean hydrogen over time. Overall, along net zero pathway, I mentioned clean hydrogen demand needs to scale 5-fold. And because production today is less than 1 million metric tons or so, production probably needs to scale 500-fold, and a lot more capital allocation needs to happen towards the sector. In our net zero modeling, about $3.4 trillion in investment need to happen between now and 2050 to scale up the hydrogen sector towards the decarbonization pathway to reach net zero. That's all my remarks today, and I'm happy to take some questions.
Very, very much for this great overview. I'm always fascinated how cheap also the Western electrolyzers can become, because I think that's really good news, and we will have to talk a bit about this. But I would be very curious, how do you come to these results? Do you look into the technology and say here there can be some savings, or here, or what? How do you come to this analysis?
Yeah, there's really two parts to our cost analysis, and that's what we do across Bloomberg. One part of the cost analysis in the near term is we do an annual price survey with both developers of projects, but also manufacturers of equipment, to estimate what the benchmark price is for an electrolysis system, with the scope being set out by us. So we go out to the industry, survey the industry on the costs, and set benchmark pricing, and that's something we will update annually going forward. And that really sets our cost out to 2025, 2026 or so, that expectation. Mm. The longer term trend is partly driven by technology cost declines, learning rates, and so on, but also by how cheap can this equipment get if we optimize efficiencies, technology improvements, we look at manufacturing scale up and automation and so on, how all these factors could drive down costs further, and we build a technology cost curve based on that. And that's how we derive these cost factors.
People, obviously, they are always thinking how reliable such analyses are. There's also an analyst world. Is there a lot of dispute about these cost projections in the analyst world, or would you say they all agree?
No, absolutely. There's a range around these numbers that everyone needs to be aware of, and most other analysts would also have different estimates. Particularly the decline until 2030 might be slower now because of the general macro environment, and what we have seen in electrolyzer costs historically is that even though there has been an expectations of cost declines, we haven't really seen cost of electrolyzer systems come down. If anything, they might be going up over the last year, just because of commodity price inflation and because we haven't seen the deployment yet. We do think, though, overall the trend is still true, that even though this might be delayed by a few years and it might not be by 2030, but maybe 2035 or so, the overall trend towards cost reductions towards that $400 per kilowatt mark or lower, it still holds true. It's just maybe the timeline is a bit more delayed than what everyone expected.
Particularly for solar project developers who might want to collocate or invest also in the electrolyzers, the question of scale is very important, because very often this low cost to reach only if you have a big scale. So how cost dependent is it? How does the cost depend on scale in your prognosis or analysis?
Yeah, our analysis is based on assuming 100 megawatt projects and upwards, right? So smaller projects will definitely be more expensive in total capex investment. Our analysis is also off-grid. So like once you connect to the grid connection costs, grid tariffs, and so on will also raise the cost of production and the cost of capex as well. That's why there is some caveats to the numbers that I just presented to you, and you need scale. So we will see more and more of these 100 megawatt plus projects going ahead. Right now, the biggest project in Western markets is 20 to 40 megawatts in size, in that range. But by the 2025, the first projects being commissioned from 2025 onwards, we think the average size of these projects is 100 megawatts and above. So we see that scale coming very, very quickly in the hydrogen market.
When I saw you had this nice graphics where you could see the cost projection in different countries. And when I saw that first, I was very surprised, because it's not so obvious that it's always cheaper in the Sunbelt. So it's also quite a lot of more north countries like Germany or the Netherlands. The costs are quite good. And I mean, I think even competitive in your graphics, a graph in 2023. 2030. Does that mean, do you think that hydrogen production will become regional? So it will not be this, I mean, we always have this picture, in the Sunbelt, hydrogen will be produced, and then there are the big ships or pipelines or whatever, or ammonia transported to the north. Yeah. Now it looks a bit more regional.
I wouldn't say that. Why the costs in some of these markets are cheaper is because electrolyzers are high capex equipment. So the utilization of them really matters in bringing the cost down today. So whatever provides you with a higher capacity factor, which in today's case is onshore wind, drives down the cost of hydrogen production lower than, for example, solar, as long as it's a one-to-one connection. Even better if you're in markets which have both good solar and good wind conditions, you can hybridize these plants to reach really high capacity factors on your electrolyzer. Those markets will probably be the cheapest to produce clean hydrogen. Think about some regions in the Middle East, some regions in Latin America as well, where you have both good wind and good solar to do that. And overall, these markets will be significantly cheaper. You will have good production availability in Spain, Sweden, and so on to produce hydrogen relatively cheaply. But there will be a cost difference between these markets and markets in Central Europe, like Germany, for example, which to some extent will rely on cheaper imports, simply because costs of production are lower in these other markets. What is important to keep in mind when we talk about the Sun Belt, when we talk about the Middle East and Latin America, is, and something that is usually left out of most analysis, is the cost of capital. And today, the cost of capital for these projects matters a lot for hydrogen because it's such a capex-heavy investment. And those cost of capital differences between emerging markets with maybe good renewable resources and Western markets with lower cost of capital but lower renewable resources really even out, in a sense that, like, even though you have less good resources in these markets, the cost of capital is so much lower that the cost of production still makes sense. Over time, as the capital costs of these equipment come down, the cost of capital matters less. And moving production overseas could make more sense for clean hydrogen production or production of derivatives from that clean hydrogen.
We might also see, let's say, a wave. At the beginning, it makes sense also in Central Europe. And then if you look 20 years ahead, again, it might shift again to other countries.
Absolutely. I mean, the first projects that we see going ahead are in markets where there's funding available for these projects to close the cost gap, right? It's more driven by the availability of subsidies than resources. And then over time, we do think projects will move more and more to markets where resources are really good.
What is your assessment of, I would call it, PV, wind, or maybe let's start with PV only, PV electrolyzer off-grid plants? Do you think that that is an option in Europe?
Over time, for sure. When you, as I mentioned, when you can hybridize, that's probably the best opportunity.
So PV
today,
and wind then?
Yeah, PV and wind together. Today, if you have onshore wind available, that will lead to cheaper hydrogen production costs. But as electrolysis system costs come down, the utilization of the electrolysis matters less and less. So there you can maybe switch to PV-only systems as well and still have very economic hydrogen production costs, just because the system capex isn't as high anymore.
Yeah, you have shown this impressive slide with this very high number, which I cannot remember, with the what investment cost is needed to really build this hydrogen economy. Is it a concern for you whether this capital will be available?
Not really at the moment. I mean, the hydrogen market is really at a very nascent stage, so we have to still see. But what we have seen is that there's a lot of interest from investors to allocate capital towards the market once the business case is proven and once the technology is proven.
That's the demand side, basically, what you mentioned, what is necessary.
Exactly.
So that is the challenge and the task for the politicians to help there. Okay, this was Adithya Bhashyam. He is EMEA hydrogen analyst at BloombergNEF. Thank you very, very much for joining. So this was our not so long but very intensive green hydrogen session at PV Magazine Roundtables Europe 2023. About the most relevant numbers from Adithya's presentation, we report, by the way, in the November issue of PV Magazine Germany, so that is available only for those who speak German. But anyway, you can read some of these numbers and find some of these graphics there. See you back soon, because we are now switching to our last session, how PV module prices will develop and where we are on the rocky road to EU manufacturing.